Very good. So I'd like to share with you a little bit about regression. I'm going to open up RStudio first, and I'm going to close this up. I'm going to start up from zero. I'm going to import a data set. The data set that I'm importing for this assignment is supermodel. And as we have seen over the past few, actually just one class when we talked about correlation, we said the correlation was good. That would show us a little bit of a relationship between, I clicked on the wrong thing. It would show us a relationship between two variables, but it wouldn't necessarily tell us anything about causality or would explain much more than simply the fact that there was either a positive relationship or a negative relationship between two or more variables if you conducted a partial or semi-partial correlation. And if those were positive or negative, or whether they were fairly small, moderate, or large correlations. And we said that there is a much more powerful analysis to conduct that is based on correlations of the variables, but also gives us the possibility to interpret the data in terms of causality. And sometimes we even refer to that in terms of predictability. So there is an outcome variable, and there are variables that predict the outcome variable. And this, in the case of this assignment, if you have a chance to go to Smart Alex Task 2 for regression, the chapter on regression, you will notice that the requirement is to load up the supermodel data and to predict salaries of supermodels by the variables age, years, and beauty. So before we even get to the analysis, it would be interesting to examine this on a common sense type basis. First of all, we need to understand what type of variables we have. So let's go ahead and import the data set, and let's open up R Commander and look at the variables in detail. See if it makes sense to even use these variables in this prediction model, in this regression prediction model. And so let's activate a supermodel in R Commander. Click on OK. So now supermodel is activated in R Commander. For the purposes of this analysis, I'm going to maximize R Commander, so you will not be able to see RStudio, but we'll be going back and forth between the two screens. The first thing I'm going to do is I'm going to look at the data. So view data set. Let's pull this guy over to the middle and let's look at it. And let's maximize this right here. Okay, so now we have a variable that's salary. We have an age variable. We have years of this supermodel being in the business, and we also have a beauty score. So some of the things that you usually like to do is check on assumptions of normality. We're going to do that very quickly. So we're going to look at the numerical summaries for all these variables, and let's click on statistics. Let's click on skewness and kurtosis to see if these guys are normally distributed data sets, and let's click on OK. And oh, I need to select the variables that are going to be included that I want to look at, and I click on OK. And so then I can go back to RStudio and I look at these guys, and I look at the mean, the standard deviation. I can start making a few interesting decisions. When I look at salary with a standard deviation of 16.02 and a salary mean of 11.33, that might tell me something that might be wrong. If I look at skewness for these three variables, I can see that salary is also, or appears to be, skewed. The ideal situation would be to correct these variables before running the analysis. In the assignment, you will notice that you're not necessarily told to do any of these preliminary activities. So let's go back to R Commander. And you can also graph some of these guys, and you can look at these guys with the graphs, checking with a histogram for normality, and also with a box plot for normality and for outliers and so forth. And one thing that you really want to do is you want to check for the correlation between these variables. And from last class, what we saw was that we could actually run some statistics here through the summaries and simply build a correlation matrix and ask all these guys to be part of the variables considered within the correlation matrix and to see how highly correlated these guys are. And I know that I can run a Pearson's R correlation because these are all numerical continuous variables. And let's go back to R and let's look at what we have. So when we correlate age with age, we see that that is a perfect correlation, and we know that a 1 is perfect correlation. It makes total sense. Age and age is the same variable. When we correlate age and beauty, we have a 0.26 of small, relatively small correlation. Salary is a moderate correlation, it's approximating a moderate correlation, and age and years has a pretty high correlation. Interesting thing about this correlation matrix is that when we're looking at these guys, only one variable with another is very highly correlated. If all the variables were very highly correlated, there would be probably an issue of multicollinearity, and that would be a violation of one of the assumptions of regression, or actually, it would be a violation of the goodness of fit of the model. So what we want to do is we want to get back to R Commander and actually run the statistics. Now, when we look at this data like that and we run the correlation matrix, it's good to make a visual inspection of the correlation between the variables, but we're not necessarily making a decision yet. We'll talk about making decisions in just a bit. So let's get back over to statistics and let's click on fit models, not necessarily clicks, just put your mouse over fit models and then over linear regression because this is a linear model, it's linear regression. And we are going to have one response or an outcome variable. And this is also referred to in some cases as a dependent variable. So it depends on some of the other variables. And we're going to indicate that salary because we're interested in a response or an outcome variable of salary that is predicted by age on the other side as an explanatory variable. So it's explained by or predicted by age. And I'm going to click on control, beauty, and ears. So what we're trying to do here is not only look at age and salary. So let's say that um, you were 18 years old and you had a salary of $20,000. You would assume that a model that's been in the business, a couple of years at the age of 20 would probably have a higher salary. And at 25, she might have a higher salary. Maybe this is not necessarily an entirely linear relationship because you would think that by the age of 40 or 50, the salary starts dropping a little bit. I'm only suggesting that. I'm not saying that, but at least within this age group or the supermodels in this data set, for this example, we have potentially a linear relationship. Another thing that we might see is that beauty could be correlated with the salary. So the more beautiful you are as a supermodel, the higher the salary. Now that may very well be true. The interesting thing about this variable is that there's a good chance that if you're a supermodel, you're also very beautiful, and the differences between the degree of or intensity of beauty may not necessarily be that big to make a difference in salary, but maybe there is a relationship, a positive linear relationship between beauty and salary. In other words, the more beautiful you are, the higher the salary. And then, of course, years. So years of experience. So how long have you been? Maybe the first time you walked the catwalk, things weren't really clicking for you. You were a little bit shy. You were a little bit, and so your salary was a little bit lower. But through the years, or the longer that you've been in the profession, or the higher the salary. And that would make sense. When I worked at McDonald's, I started off with $3.15 an hour. And then, after 1 year of working there, I got a 15-cent raise. So I went to $3.30. And even at that point, I was still paying about 40% of my number one combo without onions, which was the Big Mac combo. And so anyway, with that said, let's simply click on OK and let's see what the model tells us. Now let's go back to RStudio and look at the console. And so what this is telling us is that we have, the first thing I'm going to look at is not necessarily, well, I'm going to start right here at the top where it says call linear model. We have a formula salary. is being predicted by age plus beauty plus ears. This is the information that we're using to predict salary. And so we have a little bit of descriptives of the residuals, and you will find later on that there's quite a bit of information that is explained in regression by residuals. Coefficients may be of interest, but they are mostly of interest if we have a significant model. So to make that determination whether this model is significant, we usually look at the F statistics at a 17.7 F ratio or F statistic um, with these degrees of freedom and a p-value of less than 0.05, because again, this is interpreted differently. This is not 4.9, but this is after the period, there's at least 4 spaces before the first number emerges. So 4 spaces, 4 zeros actually, before the first number emerges. And so yes, this is smaller than 0.05. So we do have a significant model here, as we can see, according to the F statistic and the p-value. Now, once we have made that determination, we come back over here to interpret the coefficients. And the coefficients that we're interested in are the beta values that in R come underneath an estimate title or name. Now, the intercept we do not interpret, so we simply interpret the coefficients of the variables that we included into the model. So if we look at age, we can see that there is a positive relationship between um, salary and age. So apparently the older you are, the higher your salary.